Come on in and don't be late. Let's learn science with Mr. Ed U Cate. Well, g'day Year 12 Chemistry class. I really miss you guys. I hope we can get back to regular classes very, very soon. But in the meantime, you'll have to put up with my face on these videos. In this video today, we'll just go over chapter 3.4 again, which starts on page 83. It's all about the logarithmic pH scale. Well, this is the page that we're looking at right now. It's the last page of section 3.4, and it's looking at a case study of mine water. pH values can exceed the common scale of 1 to 14. Some of the most acidic water ever measured is water at mine sites. This mine in California, this ACS Publications website has shown that, has documented rather, that this Richmond mine at Iron Mountain, California, has had pH values in their waters at negative 3.6. That's pretty low, and it's lower than you think. These extremely low values can result from pyrite oxidation and high concentrations due to evaporation. The greater the evaporation, the greater the concentration of acid left in the water. Common pH methods don't work under these conditions, so glass membrane electrodes are used. The glass membrane electrodes must be calibrated for the low pH values. This can be challenging because below pH 0.5, a graph of pH values becomes non-linear. You can read more about that at that website that I just showed you. What type of acid is found in these coal mining waters? It's sulfuric acid. Sulfuric acid because it's the oxidation of pyrite that produces these really low negative pH values. Okay, this world record lowest pH of negative 3.6. What is the hydrogen ion concentration for that? We know that the pH is equal to the negative log of the hydrogen ion concentration. And by the way, you can find this on page 86 of your textbook. We know that the hydrogen ion concentration is equal to 10 to the negative pH. So they're the two equations that you really need to know. I'm sure they're in the data book, but they should be sliding off your tongue right now. pH is equal to the negative log of the hydrogen ion concentration, and the hydrogen ion concentration, when you rearrange this equation, is equal to 10 to the power of negative pH. So if we just substitute in our pH of negative 3.6 in, so that'll be 10 to the power of negative 3.6. I'll do that again. 10 to the power of negative 3.6. And we know in our maths that when you multiply negative by another negative, it's positive. So it's 10 to the power of 3.6. And when we punch that into your calculator, 10 to the power of, we're punching that button there, x with a square beside it, 3 points to the power of 3.6 equals 3,981.1 molar. Remember, it's molar, which is moles per litre, number of moles per litre. Actually, the real SI abbreviation for moles is MOL, per litre. That's pretty high molarity, considering that in class, we've really been dealing with molarities of, 0.1 molar, 1 molar, 2 molar, sometimes 3, but up to 5 molar is the molarities that we would allow you to use in class. And of course, last year we used 12 molar I did anyway, in the fume cupboard. But look at that, 3,981 molar. Wouldn't want to go swimming in this little creek. That would be bad. So what does that look like in reverse? Reverse as in, if we were given this molarity here, how do you find out the pH? Well, we know it's negative 3.6, but yeah, just like we did before, pH is equal to the negative log of the hydrogen ion concentration, and you just substitute in that value for the hydrogen ion concentration, 3,981.1, and punch that into your calculator. So negative log, you're wanting this log button here, that one there just above my finger, the log button, not the natural log button, but the log to the base 10 button is that one. Negative log, then open bracket, delete, open bracket 3,981.1, close bracket, equals, and yep, you get 3.6, negative 3.6. So there you are. That's just a rundown of chapter 3.4. But just quickly before we go into the next section, if you were working with POH, remember POH is just simply the negative log to the base 10 of the hydroxide ion concentration. You just follow the exactly the same calculations that we just did up above here for POH, and it's the same thing for working out the hydroxide ion concentration. Your hydroxide ion concentration is equal to the what are we doing here? 10 to the power of negative what am I doing? To the negative POH. I'll draw that again. 10 to the power of negative POH. Exactly the same concentrations. And remember that if you had POH, if you knew your pH, but you didn't know the POH, to find the POH, it's just 14 minus pH. And if you wanted to find out the pH when you know the POH, it's just simple. It's 14 minus POH. Just a quick example. So if the pH is equal to 2, what's the POH? The POH is equal to 14 minus the pH, which is equal to 14 minus 2. It's just 2. You can do it in your head every time. If the pH is 3, well, the POH would be 11. And I made a bit of a boo-boo there. Of course, 14 minus 2 is not 2, that's 12. But what I want to look at now is, what is pH anyway? We know it's a logarithmic scale, but what does that actually mean? pH of 2, pH of 1. Let's illustrate by jotting down a few pH values. We'll go down into the negatives. pH, we'll go down to negative 3, and we'll go down to negative 4. Let's have a look at pH of 2. We know a pH of 2 is hydrogen ion concentration of 10 to the power of negative 2. Remember, the hydrogen ion concentration is always equal to 10 to the power of negative pH value. So in this case here, when the pH is 2, you put the 2 as the power, and 10 to the power of -2 is, you can punch it into your calculator, 10 to the power of -2 equals 0.01. You don't really need a calculator for that. 0.01, which is 0.01 molar. Okay, and so if we did the same thing for a pH of 1, that's 10 to the power of -1, which is 0.1. Okay, so the difference between 0.01 and 0.1 is 10. Let's have a look at one more. Hydrogen ion concentration equals 10 to the power of 0 for pH of 0. 10 to the power of 0, any number to the power of 0 is just 1. That's 1 molar. A pH of 0 is 1 molar. And let's have a look at 10 to the -1 and 10 to the -1. Oh, don't forget, it's 10 to the -1. The pH is -1, and according to our rule, the hydrogen ion concentration is 10 to the power of negative pH. So if the pH is -1, it's -1, which is 10 to the power of 1, which is 10. So if we follow these calculations, we'd find out that when the pH is -2, the hydrogen ion concentration will be 10 to the power of 1, 10 to the power of 2 rather, which is 100. And when the pH is -3, the hydrogen ion concentration is 1,000 molar, and 10 to the power of 4 would be 10,000 molar. So as you can see, we're clearly jumping up by 10. So the difference in between one whole number pH and the next whole number pH is a factor of 10. So that's what the logarithmic scale means, the base 10 logarithmic scale. The last thing I want to look at, just for the sake of it, I did a quick Google. You can do a quick Google yourself just to double check, but I did a quick Google yesterday and found out the highest concentration that you can get for HCl, hydrochloric acid, at RTP, that's room temperature and pressure, remember that's 25 degrees Celsius, is, 12.07 molar. You wouldn't want to stick your finger in that. You really feel the prickliness there. Let's find out what the hydrogen ion concentration is for 12.07 molar. pH is always equal to the negative log of the hydrogen ion concentration. The hydrogen ion concentration in this case is 12.07 molar. And look, you don't want to look at me punching figures into the calculator again. It equals 1.08. And I did the same Google search for nitric acid. The highest nitric acid concentration you can get is 16 molar nitric acid. pH negative log of 16 molar is negative 1.2. So there you have it. You can have pH values outside of the usual range of 1 to 14. At 25 degrees Celsius room temperature, nitric acid gets to the negatives. Hydrochloric acid can get to the negatives, and we saw that the world record sulfuric acid highest concentration is negative 3.6, I think, was it? There you go. Hope that was a good rehash of chapter 3.4. Next video will be on 3.5, the Bronsted-Lowry model. Oh, by the way, all these notes that I've been taking this evening, I'll put on the OneDrive for you. I'll scan them tomorrow at school and put them on OneDrive. Have a good night. See ya.